Alright, welcome to the video for Local and Global Extrema Day 3. In this video we're really going to get into the analytical approach for finding both local and global extrema, i.e. when we're given a function and an interval, we should be able to find the extrema when we walk away. Okay, let's do this. Okay, in the last video we learned about the extreme value theorem, which said that if a function is continuous on a closed interval, then a absolute maximum and an absolute minimum exist. However, we didn't explore how to find them, and that's what we're going to do today. So the first step is we need to identify the endpoints, and those are given to us by the interval. And then we need to find critical values. And remember, a critical value occurs where f prime of x is equal to 0 or f prime of x does not exist. And it's important that that critical value be in the domain. And then what we're going to do is, from there we're going to evaluate the endpoints and the critical values. And the largest value is the max and the smallest is the min. Then we want to conclude with a complete sentence. So without further ado, let's tackle example number 7. Okay, example 7 says, determine if the EVT applies, and we have a polynomial function, and polynomial functions are continuous everywhere, and our interval is closed. The hard bracket -1, 2 is closed. So because our brackets are closed and it's a polynomial, it's continuous on that interval. So the EVT applies, and we can start tackling finding the extrema. So the first thing we're going to do is we're going to find f prime. So f prime of x is equal to 12x to the cubed minus 36x squared. And we will use that derivative to find critical values. So 12x to the third minus 36x squared should be set equal to 0. And if we factor that out, we get 12x squared times x minus 3 is equal to 0. This gives us critical values of x equals 0 and x equals 3 using the zero product property. So step 3 for the closed interval method is to find the function values at the endpoints and at the critical values. So we need to find out what is f of -1, because that's an endpoint. We need f of 0, because that's a critical value, and f of 2, because that's the other endpoint. And we would include f of 3, but 3 is outside the interval, so we're just going to ignore it for this problem. And we can evaluate these very simply by plugging -1, 0, and 2 into the original function, and we find that f of -1 is 15, f of 0 is 0, and f of 2 is -48. And we can see this is our minimum and this is our max. So we draw a conclusion in a complete sentence on the interval -1 to 2. F of x has an absolute max of 15 at x equals -1 and an absolute min of -48 at x equals 2. Alright, there's our concluding statement. That's the closed interval method for finding extrema. To recap, we find if the EVT applies, and then if it does, we find the derivative, set the derivative equal to 0, find our critical values, test the endpoints and the critical values, and then draw our conclusion. Example 8 is so close in style to example 7. I want you to take a shot at tackling that one on your own. Go ahead and pause the video. I will write out my solution and then you can check your work against the solution provided. Go ahead and pause it now. Alright, so the function is continuous on the interval, so the EVT applies. We take the derivative and then we do some fancy factoring and cleaning up, and we set it equal to 0. When x is 1, we get an answer of 0, and when x is 0, the derivative does not exist. And then we test the 3 endpoints, and we're able to draw our conclusion. We get an absolute max of 0 at x equals 0, and an absolute min of negative 28 at x equals 8 for that interval. Alright, example 9 is very similar in style, so let's continue tackling this. First off, we see that the function is continuous. Sine and cosine functions are continuous. And what we have is we need to first take the derivative and then set the derivative equal to 0. So setting this derivative equal to 0 takes a little bit of fancy trig manipulation. First off, I'm going to replace sine 2x with the double angle identity, 2 sine x cosine x. And then there's that 2 at the end. And then I'm going to factor out a 2 cosine x, and that gives me 1 from the first term. And to that we add thing jumped. We add 2 sine x because we pulled 2 cosine x out. Using our zero product property, we can either say that 2 cosine x is equal to 0, giving us x values of pi halves and 3 pi halves, or we can say that 1 plus 2 sine x is equal to 0. Solving that, we get values of 7 pi over 6 and 11 pi over 6. So there's our 4 critical values, and now we just need to do the candidates test on it, and we're going to test the endpoint, our critical values of pi halves, 7 pi halves, and then our other endpoint of 3 pi halves. And we would test 11 pi over 6, but that's outside of the interval provided. And relying on our calculator, if we wish to, we could find all of these values, and we get our maxes and our mins. So it looks like our maximum occurs here, and our minimum occurs here. So, did I write 7 pi halves? That should have been 7 pi 6. 7 pi 6. Alright, so draw your concluding statement. F of x has an absolute maximum of 3 at pi halves and an absolute minimum of negative 1.5 at 7 pi 6 on the interval 0 to 3 pi over 2. Alright, sometimes an interval is not given to us, and when that happens we may not be able to find what's going on without first drawing a sketch. So example 10a, through some analysis of the curve you could see that the denominator restricts our domain, and we get the 4 minus x squared has to be greater than 0, which means that x is pinned between negative 2 and 2. And we use that fact to help us draw the graph. X is pinned between negative 2 and positive 2. If I plugged in f of 0, I would find that I get 1/2, so f of 0. And playing around with a bit more or turning to my calculator, I could sketch the graph based off of that information there. And that's what that curve looks like. And we want to find where the absolute maximum is and where the absolute minimum is. Well, because the interval that it's pinned between is -2 to 2, the EVT fails us, and we don't know for certain whether there will be an absolute max or an absolute min, but looking at the drawing, we can see that the curve comes down to a minimum right there. And if we wish to, we could prove the minimum was there by taking the derivative and setting the derivative equal to 0. So we get -1/2 4 minus x squared to the -3/2. Apply the chain rule, and we see that there's critical value at x equals 0. There would also be critical values at plus and -2, but that's outside of the domain, so we don't include those. And we can run this through the equation and find that f of 0 is equal to 1/2. And looking at our graph, this is the absolute minimum. So, taking a drawing approach on part B, we can sketch this piecewise function. 5 minus 2x squared is a parabola that shifted up 5 units. 1, 2, 3, 4, 5. And it has a vertical stretch of -2, or we should say vertical stretch of 2 and a reflection. So our parabola looks something like that for less than or equal to 1, and then for the second piece of our function we get a line of slope 1 and a y-intercept of 2, and it looks like that. So from this, it looks like we have some local extrema going on there and there. It looks like we have a local max and a local minimum. So we can run this by. F prime of x is taking the derivative. We're going to get -4x if x is less than or equal to 1, and 1 if x is greater than 1. And so our only critical value for this, you'd think, is x equals 0, but we also have the critical value of x equals 1, because at that point the derivative does not exist. So if we test both those values, we find that f of 0 is equal to 5, and f of 1 is equal to 3. So we get our local max and our local min. So local max of 5 at x equals 0, and a local min of 3 at x equals 1. All right, the final example. Sometimes we may need to use our calculator. As we see here, we have a continuous function, and when we take the derivative of this continuous function, we get f prime of x is equal to 1e to the -x plus xe to the -x, chain rule, times -1, minus 2. If we clean this derivative up, we are going to get e to the -x minus xe to the -x minus 2, and we want to set that equal to 0. And taking this equation and setting it equal to 0 would be difficult to do analytically by hand. So we rely on graphing it and using the 0 function on the grapher. And when we do that, we find that this equation gets a critical value of x is approximately -0.3748. And we're going to store that as the value b. So when we run the candidates test on our calculator, f of -1 gives us approximately -0.71828. And f of b gives us approximately 0.204, and then we test the other endpoint, and that gives us approximately negative 0.1632. So that we relied heavily on the calculator, a lot of decimals there, and we want to be accurate with that. I'll try to remember to cover how to do that on the calculator in class. Feel free to remind me. So we draw our conclusion. F of x has an absolute max of approximately 0.204 at x is approximately negative 0.3748, and an absolute min of approximately negative 1.632 at x equals 1.
Look at those cheeks.
All right, hopefully after watching this video you should have a clear understanding of how to find the absolute or global max and min using the candidates test, or as we called it, the closed interval method for finding extrema. You want to find the derivative, set the derivative equal to 0 to get your critical values, and then test the values of your critical values and endpoints to see which is the max and the min. Thanks for watching.